Okay, so now when we know what are the different quantum numbers, let's try and see the applications and how we can find out through an example. Okay, so I have this written down. So magnesium, say magnesium, we are trying to find out the electronic configuration. So we are well versed with this at this point. So magnesium has 12 electrons, so this is how we arrange it, right? 1s2, 2s2, 2p6, and 3s2. Okay, now we also know how we can arrange the box diagrams, right? So we have a box diagram from each of these. Now for this P, we now see that, okay, this has 3 different rooms of P suite has 3 rooms. Why? Because it has 3 orientations, right? So Px, Py, Pz. There were 3 orientations possible for the dumbbell shape, and that is why you have three different rooms in here, right? And how do we identify those rooms? By the magnetic quantum number, right? Which gives you the orientation. What are the different things? What are the different number possibles? It can go from minus L to plus L. What is the L of P? The azimuthal quantum number of P is 1. So magnetic quantum number, since it can go from minus L to plus L, for this case it will go from minus 1 to plus 1. So it goes from minus 0 to 0 to 1, right? Okay, now let's try and find out the 4 quantum numbers associated with this electron, this red, the one represented in here, red. Okay, so I've written down it here. The principal quantum number of that electron will be 3. Why? Because this is the 3s orbital, right? So the principal quantum number is 3. The azimuthal quantum number is 0 because the azimuthal quantum number associated with the orbital s is 0. The m automatically becomes 0 because that is the only one possible, and the spin is minus half. Okay, so this is how we find out the 4 quantum numbers. Now let's find out the 4 quantum numbers of this purple electron. Okay, similarly goes for 3, 0, and 0. In this case, the spin is different, right? One is a clockwise, like the plus half, and the another is a minus half spin. Okay, so generally the clockwise spin is given a minus half, and the anti-clockwise is given a plus half. But for now, for keeping it easier, we are just representing the down as minus half and the up as plus half. Okay, just for simplicity's sake. Okay, now let's look into this blue electron in here. So it is an electron from the 2s. So this becomes, the principal quantum numbers becomes 2, L and M still remain 0, right? Because it's from the s. Okay, the s, the spin quantum number is minus half because it's spin down in here. Okay, all right. Now let's move to another one, which is this green one, which is from the 2p orbital. Now all these were from the s orbital, right? So the L0. Now we move to L1 because it's a 2p. So the principal quantum number is 2 because it's 2p. The azimuthal quantum number becomes 1 because it's p. L of p is 1. The magnetic quantum number is minus 1 because it's from the first one. If it were from this one, the magnetic quantum number will become 0. If it were from this, the last one, it would have become plus 1. Okay, but in this case it's minus 1 and the spin is plus half. Now you see we have like 4 electrons, just for example. You can write down the 4 quantum numbers associated with all the 12 electrons. Even when you write all of them, you will see none of those electrons will have the same set of 4 quantum numbers. Okay, in this case you can see like these two will have 3 of them similar, N, L, and M, but the S becomes different. And this will be true for all the electrons. You can have 3 similar, but the last one will become different. You can have the maximum number of similarities can be 3. It cannot have 4 similar. It can also happen that all of them are different. Okay, it can also happen like that. Say for if you see the down spin in here of the 1s and you see the up spin in here, up spin in here, 2p, the n is different, principal quantum number, because the principal quantum number in here is 1 and in here it's 2. The azimuthal quantum number is different too because the azimuthal quantum number is 0. The azimuthal quantum number is 1 because it's a p orbital. The magnetic quantum number is 0. The magnetic quantum number is 1. the spin is plus half, the spin is minus half. So you see, it can also happen that all the 4 are different, but none of them will have all the 4 similar, okay? So this is basically Pauli's exclusion principle. Now, we didn't see any example from the D, so let's see as an example from the D. So let's say you have a 3D arrangement, which is this, okay? Now, you have the last electron getting here, okay? So can you tell me all the quantum numbers associated with this? It's 3D, so n becomes 3, L becomes 2 because it's the d orbital, and d orbital has an azimuthal quantum number of 2. The m becomes 1 because this goes from -2 to +2, and this happens to be a 1, and the spin quantum number is plus half. Okay. Similarly, you can find out the quantum numbers for any electron, and you will see no matter what happens, Pauli's exclusion principle holds. No 2 electrons will have all the 4 quantum numbers similar for an atom. Okay? Awesome.